Okay. So why switch to a new version of Ada? That's not necessarily an easy sell. I recognize that. There are reasons why you would stay with the version that you're on, but I'm going to at least give you a sales job on why you might want to consider that, at least. Okay? Now, why do that? Well, because changing people is difficult and expensive. And if you're familiar with Gary Larson's Far Side, here's Alan pulling out a bigger brain in the middle of the test. If we could do this, great. Everything would be fine. This is what we cannot do. A later version of Ada is actually something that you can control. And we expect, although we are not always in the case of making that decision, we expect that the productivity gains will outweigh the risks. Obviously, that's your choice. That's based on your application and your project and how long it's supposed to go and how much risk there would be to change compilers. And because it basically is changing a compiler when you upgrade to a newer version. We understand that. Of course, we expect the gains to be a matter of productivity, which is money, in other words. Everything we talk about really ultimately comes down to money. So we expect the productivity gains to outweigh the risks. But again, that's what I'm saying is up to your situation. Only you know if that's really is the case or not. But at least I can make the case for you that the language has added a lot of expressive power, and hopefully those risks would be outweighed by the gains in productivity that result from that. So if you look at the Ada evolution, if you think about Ada 83, that was really a very big jump. It was putting together in one language what was piecemeal available in various other languages. Some languages had modules, for instance, and a few languages had things like exceptions. PL1 had exceptions, for instance. But that was putting together a lot of stuff that was new to be and really novel to be in one big language. Putting concurrency in the language was not unique by any means, but was for a mainstream language was certainly unusual. Exceptions were almost a research topic. Should you have resumption semantics or should you have termination semantics? PL1 had on error, so you went off and executed a little routine in response to an exception, and then went right back to where you were. As you've noticed, perhaps most languages nowadays use termination semantics, where you don't go back to where you were, because it's really just too expensive to implement that. You have to save off the registers and do your stuff and then save them back again. And right, so it was a big change in terms of programming language technology, with a lot of, I think you would agree, benefits that result from that. It was a big deal. We think back of it now as kind of an ancient language, but it was a really big thing to put together. And why the compilers were so slow. It's kind of like Ada 95 and so on made big advancements. An Ada 83 compiler, when it was brand new, was kind of like a C++ compiler when they were brand new. They were not the best compilers on the planet because they were doing lots of new stuff. And if you look, therefore, at the other parts of Ada 95 and Ada 2005 and so on, they've added some things that were, in some cases, very big gains in expressive power. Some things were small, some things were big. Adding efficient synchronization, protected objects in particular for Ada 95 was a huge advance in expressive power. Using them for both concurrent programming, but exceptions and not exceptions, interrupts and so on. A big change and a big advance. Full OOP, better access types, child packages, the annexes, the systems programming annex and the real-time annexes. This is a big thing, a big change. And I kind of like I didn't make up that arrow, that's just a PowerPoint arrow. I like the arc of that though, because you can see that going from Ada 83 from something else was a big change, going to Ada 95 was a big increase in expressive power, and it's starting to flatten out a little bit. I don't know if that's a good thing or not a good thing necessarily. 2005 added some big things, multiple inheritance, so on, and containers, more real-time stuff. The Ravenscar profile was codified. Big stuff. And Ada 2012 has, again, some big things that are added to it. My favorite personally is contracts, but some other things are very important as well. So the language keeps adding stuff that gives us more and more expressive power as you go. And that's what I'm saying is the key to the productivity, is the fact that you can say things better than we could say in the past, or say things that we couldn't really say at all in the past as well. I'm thinking of parallelism at the statement level, for instance. That's coming. So if you haven't seen contracts before, I bet some of you have. I know some of you have, but I bet many of you have. But just to make sure we're talking about the same thing. When I talk about contracts, I'm talking especially about subprogram contracts, the pre and post conditions. There are other kinds of contracts that we can express, but these are the most obvious ones that people think about. Not introduced by Ada by any means. Eiffel had these a long time ago, and Eiffel didn't make them up either, for that matter. But Eiffel was, well, basically the first big language that had them. And they are very, very similar to what we do in Ada as well. So for my push routine here for my stack, I'm saying this is the value of whatever content type it is. This is what I want to push onto this stack. Well, the precondition, of course, is you don't push onto a stack that's already full, right? And likewise, the postcondition then, which is our low-level requirements, the postcondition is, well, it won't be empty now, and the top of the stack, which is just another function call, the top of the thing that you're pushing onto is now the thing that you wanted to push onto it, right? You said push this onto the stack, it's now the top. The number of things in the stack, the extent, is one more than it was before. So this old, tick old says, give me the value before you pushed. And then finally, we can say everything else in the stack that was there before is unchanged. Our push routine didn't add some other arbitrary value or reorder them or anything like that. Everything is the same as it was before, plus this new value. And that's really the trick. That last one is the trick of coming up with good post conditions, because you might not have thought about saying, and everything else is unchanged in addition to this one that I just added. So having complete and really expressive low-level requirements is the key to writing good post conditions. But now it's codified in the code, it's checked at runtime, it's never out of date. It's not like comments like we had to use in the old days where your comments are almost instantly out of date. Right? It won't compile if this isn't correct anymore. And it won't pass at runtime either if it's not anymore. So these are just functions, Boolean functions that you call in your post conditions. Checked at runtime. And that's why I think it's such a big deal. All those things I just said, it's always up to date. It's checked really, it's part of the code. It's checked at runtime. It's a big, big improvement. So for Ada 2020, we think it's Ada 2020. The X is probably 0, in other words. Some of the big things are fine-grained parallelism, statement parallelism in particular, and I'll show you an example of that in a second. More contracts are going into Ada. They're coming from Spark in particular. Some of the stuff that you might say in Spark is now codified into standard Ada in particular. There are richer expressions. There's a new profile near and dear to my heart that's based on Ravenscar. I'll show you that, and some other things as well. So when we talk about statement-level parallelism, primarily that's parallel loops and parallel blocks. So the idea is that you would have, in this case, I've got an expression pointer for a tree. And so we pass this thing and say, well, I want you to traverse that. Oop, that didn't work the way I wanted. We'll traverse that, and if it's a binary tree, then in parallel, we'll traverse the left side and the right side, and we'll print out this put line thing at the same time. Each one of those little parts being a separate thread. Not a separate task, but an actual thread underneath the hood. Likewise for loops, we've got a parallel stuck in there before the for loop that says each one of these iterations is its own little thread that should go off and do something in parallel. Depending on what your architecture is, it'll either do it literally in parallel, or maybe it does it sequentially if you're on a monoprocessor. But the idea is at least it's potentially done in parallel there. And if you're familiar with the richer expressions I was just saying a second ago, the right-hand side of that assignment statement there is a quantified expression that says all these values over here have to be true before the result is true. So we're just walking down that list, that first column of the array, and setting that to be the true or false based on everything else in there. So that's an Ada 2012 expression. That was one of the richer expressions that I was mentioning a moment ago. All right. And that profile based on Ravenscar is named Jorvik. That's a Y there. If you're familiar with Ravenscar, Ravenscar was a small, it still is, a small village in the northeast of England, on the coast of England, north of a place called York. And the Viking name for York is Jorvik. So the joke here underneath the hood is Jorvik is like Ravenscar. It's close to it, in fact, but it's bigger. And that's the idea, because basically we've relaxed some of the things that Ravenscar requires you to do and given you more expressive power as a result of that. In particular, though, it's not a replacement for Ravenscar. I need to stress that. Ravenscar is still there, and it's still part of the language, and it's still meant for you to use, especially if you're going to be certifying. So if you need to have a certified application where you do the actual, DO 178A and so on, B and C in this case, for level A, for instance, we expect that you would still use Ravenscar, because the runtime for Ravenscar is slightly smaller, slightly simpler, And the source code as well in in a Ravenscar application, the source code is simpler as well because you have to adhere to a certain number of restrictions that we've relaxed in this other profile. So if you're doing certification, use Ravenscar. If on the other hand, what you need is real time and you want predictability and you want schedulability and all these good things, but you're not going to certify it, then this other profile named Jorvik is the thing to consider. Still useful for real time, still useful for embedded, but probably not going to be certified because again, the source code, the application level in other words, but also the runtime itself is going to be a little bit more complex than in the Ravenscar case. So many or if not most of the coding designs that you would use with protected objects, the idioms in other words, are now available under the Ravenscar ++, if you will, the Jorvik profile here, as opposed to Ravenscar. Ravenscar doesn't let you do some of the things that you might want to do, for good, very, very good reasons for that matter. And in the Jorvik profile, we allow that. But as I said, you don't lose the good stuff, you just add some expressive power. So for example, here I've got the body of a protected object that defines a bounded buffer. In Ravenscar, because you want to have two entries logically, one for putting and one for getting, both of which can block. In the Ravenscar approach, you would actually have two separate protected objects, one for the putting and one for the getting. But the normal idiom is to have two entries in one protected object. And now under the Jorvik profile, you can do that. So you can have multiple entries per protected object, multiple queued callers per entry, if you wish. And also the barriers can be more expressively powered. You can put more in them than you could with just the Ravenscar. So this is the way that, this is cut and paste from one of my bounded buffer examples that I use for teaching people. This is directly supported under the Jorvik profile. All right. Now, is all this more productive? Over the years, the answer has been yes. And you heard about one of them, the VDC research results. But over time, there have been studies showing that Ada is more productive than C in particular, but other languages as well. And I would argue that it's still the case, and the VDC research document highlights that, backs that up. Which brings us to Spark. And as my little diagram there is meant to show, Spark and Ada are kind of merging. The stuff that's in Spark tends to move into Ada, and there's some things obviously within Ada that move into Spark because the Spark subset is growing over time to where it's almost full Ada nowadays. That was my problem with Spark in the old days. I was a big fan of Spark, with 8083 for that matter, and 8095 versions of Spark. But it was such a small subset that it was too painful for me to program much in it because there were just so many things I wanted to use that you can't use in those older versions of Spark. But it's almost the full language now. It's got tasking. There's Ravenspark, for instance. It's got generics. So it's a very powerful language. And in fact, I would say that Spark is really my favorite language, to tell you the truth. Spark also serves as a good test bed for Ada 2020. There are things that we want to know really do work, and we first implement them in Spark, and either they go in or they don't based on their results. So what can we prove statically? And you may have heard parts of this. I just want to reinforce it. The first thing you can prove that you don't have runtime errors, which is a huge thing. Right? No exceptions in your code, no buffer overflows, no invalid array indices, which means it's finally safe to turn off the runtime checking when you deliver your final application. Like the vast majority of us, we debug with checks on, and then we turn the checks off and deliver that, which means you're delivering something that you haven't really checked. Right? It's a different binary. And to the degree it correlates, then you're safe. Now it's finally safe to turn off the exception checking because you've proven that they won't happen. Yeah, big deal. You can also prove the data and information flow. You can prove in particular that you don't have any uninitialized variables, no assignments that don't have any effect, and so on. You can also prove that the data goes where you think it's going. So if you're doing a security application, it would be eventually possible for you to say, I know where all my data is going, and I know I'm not having any leaks between components. Right? Possible too. Functional correctness at the unit level, that's that low-level pre- and post-condition stuff. The post-conditions define the low-level requirements. Now you can prove per unit that you've got those low-level requirements met. Because the post-conditions, if they're completely written, are the low-level requirements. That's your unit tests, essentially. And then finally, arbitrary properties. Things that aren't functional necessarily per unit, but that are still nonetheless very important. For example, Here I've got, again, my low-level requirements expressed as the pre and post conditions. And then I've added a couple of contracts there, the global, which is going into Ada with slightly different semantics, but the idea being to talk about what the global variables are. In this case, we don't reference any global variables, and so we can explicitly say that. And we can also say what the value of this, the stack, what its value depends upon. It depends upon itself, essentially, and the item that you pass into it. And these are all verified statically. Right? Instead of doing them at runtime and checking them at runtime and getting an exception, Spark will either prove or not, based on how your code is written, that those two do in fact hold. Right? So that's the big deal here. We're doing it statically rather than at runtime with exceptions. Which means you pass the test the first time. I mean, I personally wouldn't get on an airplane that's never been tested. Right? But the fact that you can prove that these things hold mean that you don't spend all the money churning on trying to get the test to pass, because that's where we spend most of our money, on the testing of the things. They should pass the first time now. I don't know if you can read that. That's a Zimbabwe note. It's a $100 trillion note. So when I say proving abstract properties, if you've gone back to the back there, there's a little demo running on a slightly different board. It's the same demo of the train system. And you can push the soft buttons and it'll launch trains and move the switches so that the trains go in different patterns. The point is, in Spark, we've proved various properties about the code itself at the unit level. So my move routine says, give me a train ID and where you want to go, and I'll tell you the result of that. Right? The result being either go full speed or slow down or keep going as you are or stop. That's the value that comes back out of the results parameter there. So the precondition is that's got to be a good train, and it's a valid place to go in the first place. But also that at most one train is on a track, any given piece of track, and the safe signaling is true as well, that both of those things hold. Those are abstract properties. They're not functional properties about the thing. That's the first two parts of it. They're just purely abstract things that says we want to make sure that we never ram two trains into each other on the same piece of track, for example. So that has to be true on the way in, and it has to be also supported on the way back out. So our post condition says, still, we have at most one train per track, and still we have safe signaling, so we're not about to direct any two trains into each other as well. So that's what I mean by the abstract properties, and those were proven in this particular demo in Spark. And I was told by one of our vendors who does trains that they don't do that much proof. I don't know if that's, I think he was kidding me at the time, but I hope anyway. So how reliable is it? How reliable can you be? Multos is a good example. Multos is a certificate authority. It's basically an operating system for smart cards. They had 100,000 lines of code. 5 defects is what you would expect. They had 4 in the first year. Right? The industry standard is 5 per 1,000. They had 4. Right? Corrected under a warranty, too. So extremely productive, very, very reliable. In terms of productivity itself, the industry standard is 10 lines of code per day in any language. And I'm talking fully documented, fully tested, out the door, boom. The industry standard is 10 lines of code a day. Right? They hit, 28 lines of code a day. So Spark doesn't slow you down. This one is all about money. Basically, on the C130J case, they saved a lot of money doing the hardest kind of software there is, level A of DO-178. Magnitude of code quality improvement, and software costs were half of what it is for the easy software. So they're doing the hardest stuff, and it costs less than doing the easy stuff. And you don't have to do all this on your own, as you've seen. And in fact, Jamie was back there in the back at one point waving this thing. This is that same document. We will help you do this. You don't have to go off and bite off a whole chunk of everything and do it on your own. We'll show you how to do this and talk you through it, so to speak, with this document here. So to take away, Ada gives you a lot more power, a lot more expressive power as you look over the curve. Again, whether or not that's worth the risk is up to you, because I'm not saying it's not without risks. But you can start playing with things. If you use the switch GNAT 2020, you can start playing with the Ada 2020 stuff. As you saw, the Spark takes a big step forward and gives you a lot more power by statically verifying instead of dynamically verifying things. And again, with examples there, you've seen that you can be a lot more productive and save a lot of money if you use the best technology, which I think to be Spark. So I say my point being that the risks are worth the gains. potentially. Questions?